Hello everyone and welcome to this new video where we're going to be talking about the RNNs or recurrent neural networks in simple terms and also using an example to better understand this concept. So what is an RNN and why do we use it? In classical neural networks we cannot handle sequences because each input is treated independently. So the RNNs are used when the past information influences the future predictions or the data has temporal or sequential structure. So we need the memory of the previous steps. These RNNs are designed to model the data where order matters. Let's see this case in the financial market. Would we rather predict tomorrow's price of a certain stock or security with today's price, or it would be better to predict tomorrow's price with today's price and also 30 prices of the last month? Obviously it's the second option, and because we have and, so we cannot read today's price, yesterday's price and the day before that independently because they influence each other. This is where RNN comes handy because it basically gives the neural network a memory of the previous inputs. So let's see this at a high level architecture. This is a normal neural network and here is a recurrent neural network. So basically this arrow here where in each hidden layer we use the information of the previous hidden layer or input layer. Let's zoom here to this part. So unfolding it is basically like this, where this is the input. It goes into the hidden layer with weights biases, as we already know, and then we use a new weight, a different weight than the one we used here, to go to the next hidden layer. We also use the next input. We pass it to the hidden layer also using the same weights and biases used in the first one, plus the previous hidden layer multiplied by this weight, and we do that for each step. Let's look at it with a better wordings. The core idea is that at every timestamp the RNN takes the current input and the previous hidden state or the memory, and we can output a new hidden state, or we can optionally make predictions. So in this case we can have multiple outputs or just one, depends on the context of our problem. So mathematically it is the activation function of the weight of the hidden layer multiplied by the previous hidden layer plus the weight times the input plus of course the bias, or it's this one. So let's set up an example where we need to predict the stock price at time n+1. We have in the last 4 days the price was 1 and the next day 2, 3, 4, and let's say the n+1, the actual is 5, but the model doesn't know that yet. It needs to predict it. So we input number 1 here, we go to the hidden state by multiplying it with the weight plus the bias, and we get a certain number here after activating the function to introduce nonlinearity, and we pass it using another weight and also the second input, so number 2 in this case, multiplied by the same weights and biases that we used here, and we pass it by multiplying it using a weight that is the same one as the previous one, so this W is the same as this W. Let's look at this example for better understanding. So let's make a forward pass where the input is 1, 2, and 3. The target, as we said, is 5. The initial hidden state is 0. This is the initial hidden state, this first one, because we don't have here a hidden layer. So we will use the activation 10H. We will use MSE as a loss function, learning rate 0.1. These are the initial weights and biases. So the first forward pass, before doing any training, we will compute the first hidden layer. Let's say it's the weights multiplied by the input plus the weight multiplied by the previous hidden layer plus the bias, and we'll do that for each step until we get this output 0.96, and then we calculate the loss. We see that it's 16.32. So we have a large error because the target was 5. Okay, now we need to do the backpropagation, but using an RNN, obviously it's different because we're backpropagating through time. So we are going from the loss function to this direction and going here, and because this depends on the previous hidden layer, we go also here, and because this one depends on the previous one, we go here until we reach all the weights and biases, the initial ones. So before applying the chain rule of the derivatives, it can be written as the loss at the fourth time step is dependent upon y hat due to the fact that the loss is calculated as a function of y hat, which is dependent on the previous one. So this is the first one, the second one, the third one, and this is the fourth one. So after performing the backpropagation through time, we got, and also multiplying it by the learning rate to update the parameters, we get these values, these new weights and biases. If we use them for a second forward pass, the new output would be 2.5684, and remember it was only 0.96. So we are closer to the real value, which is 5, and the loss also decreased by a lot, from 16 to 5. So we are in the right direction. We can say that the prediction moved closer to 5 and the loss decreased a lot after just one weight update. This shows how the backpropagation through time, a gradient descent, starts to push the network to the right direction even from a poor initialization. But we can see a very, very huge problem. This is the formula of the backpropagation. Because it depends on the weights of the previous step each time, and we said that the weights and biases are the same. Remember here, we said that the weights are the same. So here it depends on the weight, the weight, the weight, the weight. Let's say that the weight is look less than 1. Let's say it's 0.02, or it's very close to 0. This would be very close to 0 because we're multiplying by basically 0. This one right here also, this one also, and this one also. So 0 plus 0 plus 0 plus 0 is 0 here. So the gradients would shrink to 0. So the model cannot learn long-term dependencies. These are only for steps. Imagine if there were 2000 step or even more. So early information would get lost after approximately 5 to 10 steps in this particular case. This is what we call the vanishing gradient problem. Now let's imagine the opposite, that these weights are bigger than 1. Let's say this weight is 100, so this would be multiplied by 100, or adding 2 zeros, the same here, same right here, and same right here, and then adding them up. This would lead to what we call exploding gradient problem, or like the gradients would be very big, that the loss becomes none, and we say also that the weights would blow up and the training becomes unstable due to the very high values that we have. This is the exploding gradient problem. So what's the solution? If it's bigger than 1, we get a big problem, and if it's less than 1, we get also a big problem. The solution is using another improved form called the LSTM, or the long short-term memory, where we have a slightly improved structure or architecture, where we will introduce gates, cell state, and controlled memory flow, which allows it to remember information for dozens or even hundreds of steps. So we will see this in the next videos, but you can ask, then why are we learning RNN if it has this huge problem? We would say because it's good to know this kind of architecture, so you know the basics in the deep learning and how it was evolved through time, so until we reach this step of advanced AI architectures. That's it. Thank you for watching. Please subscribe and like the video if you like it. Thank you.